This is the second lecture in a 5-lecture course on general relativity. Today we are going to discuss space-time curvature and the stress energy tensor. And so you will recall that towards the end of the first lecture, we had introduced the concept of a covariant derivative. I'm going to resume with that slide for continuity. So once again, recall that the bold-faced V is a 4-vector in a 4-dimensional space-time. And we realized that in a general case, when we take the derivative of this vector with respect to space-time coordinates, let's say x nu, then that derivative by differentiation by parts will first act on the components of that 4-vector, namely the v mu's, but also in the second term act on the basis vectors themselves. So in Euclidean geometry in Cartesian coordinates, when the e mu's are all fixed both in magnitude and direction, the second term, namely this term here, goes to 0 identically, which is why we are used to dealing with only the derivatives of the vector components, never worrying about this second term. However, even in flat space or flat space time, when we use curvilinear coordinates, this derivative of the basis vectors can be space-time dependent and not 0 identically, in which case we have to account for this second term as well. In curved space or curved space time, in general, this second term will contribute. So this was the origin of a term which we introduced, namely the Christoffel symbols. And that is because the derivative of a basis vector, as shown in this blue box, can be expanded in terms of the basis vectors themselves on the space-time. And these Christoffel symbols, namely the gamma, alpha, mu, nu, are the expansion coefficients. To wit, if you want to take the derivative of, let's say, E0, where 0 is the time basis vector, so the basis vector along the time coordinate, with respect to x axis, so that would be nu of 1, because that is the x coordinate. In that case, you can expand such a derivative in general in terms of all of the basis vectors, so E0, E1, E2, E3, and the Christoffel symbols that will allow you to interpret this derivative will have mu set to 0, the time coordinate, and nu set to 1, representing the x derivative. The alpha here will be summed over. So alpha will also, in step with the basis vector, go from 0 to 3 in steps of 1. But this is a very powerful utility, because it allows us to go back to equation 1 and express the general space-time derivative of a vector solely in terms of an expansion over basis vectors, the e mu's. This is what we try to do in the steps following this blue box, namely in equation 2. So bear with me here as we go through this carefully. So beginning with box 1, the equation in box 1, all we do, so we go back to equation 1, and what we do to work out equation 2 is first replace this derivative of the basis vector in terms of this expansion in the 4 basis vectors. So that gives me 2 of these terms. The first one here is the same term verbatim as the first term on the right hand side of equation 1. It is the second term where we replaced the derivative of the basis vector in terms of these Christoffel symbols and their sum over the basis vectors. For the remaining few steps, I am going to replace the first term with just these square brackets times e mu, because that is going to remain the same, and it allows us to focus on the second term, which is where we will simply manipulate some of the indices for convenience. So, the next thing we will do is we will substitute in equation 1 this Christoffel symbol expansion for the derivative of the basis vector. The first term will be retained verbatim. So, that is why in the following step you will see this replacement, and in the next couple of steps I am going to rearrange the indices on the Christoffel symbol and the vectors so as to be able to take out E mu as a common term from these two terms. The purpose of that will become evident in a few seconds. So, in the third step here, I retain this sum over beta, but I replace the alpha sum with the sum over mu, and that is allowed and legitimate because alpha is a dummy index, because it is summed over using the summation convention. So, regardless of whether you sum over alpha going to 0 to 3, or in this case mu going from 0 to 3, the answer remains unchanged. When we do that, we are able to recognize that E mu now is common to both of these terms, and therefore can be taken outside these braces. That leaves the original derivative of the vector components in the first place inside the braces, and in the second place we have this multiple of the vector components and the Christoffel symbols, but actually summed over the beta index. This braced quantity is what we define as the covariant derivative of the vector components with respect to x nu. And this definition is important because this is the general definition that will be used to express the derivative of any force spacetime vector. So, that is why we again encapsulate in this red box. So, we say that the covariant derivative of v mu with respect to, so v mu semicolon nu is defined as the covariant derivative of the vector components v mu with respect to x nu, and this is an important quantity that is required to define the spacetime derivative of any vector, which is why we rewrite it again in this red box, namely the covariant derivative of v mu with respect to x nu is equal to the ordinary derivative of the same vector components v mu with respect to x nu, and the comma here denotes an ordinary derivative, plus this interesting term which is the contraction of the Christoffel symbols with respect to the vector components. Here again we have summed over the beta index across all four spacetime indices. Let us now show an example of Christoffel symbols, that is how they are in terms of space-time coordinates for a case where, because it is the first example, I will limit myself to two space dimensions. So, the coordinates are going to be x and y Cartesian coordinates, but we are going to make a coordinate transformation from those coordinates to polar coordinates r and theta. But because we are dealing with Christoffel symbols, let us recall that under any coordinate transformation and not just Lorentz boosts, you can relate the basis vectors in the S prime frame to the S frame or the unprimed frame in this fashion, where again there is a summation over alpha prime. The inverse of this coordinate transformation, you can convince yourself, is expressed as in equation 2. Namely, the E alpha prime is equal to lambda mu alpha prime contracted with E mu. We will see again an example of this expansion in a minute, but this also tells you that this is utilizing the fact that the coordinate transformations obey this inverse property, namely that if you contract it with its inverse, you get the Kronecker delta, or just in matrix from the identity matrix. Now, for this two-dimensional coordinate transformation, the equations of transformation are simple. It's just that x is equal to r, the radial coordinate, times cosine theta, the angular coordinate, and y equal to r times sine theta. Knowing that the elements of this transformation matrix lambda, alpha prime, mu are ultimately just derivatives of the r and theta coordinates with respect to the x and y coordinates respectively, you can tap into this coordinate transformation equation to work out that all of the elements of this transformation matrix are as simple as given in this final matrix, namely cosine theta, sine theta, and then negative sine theta divided by r, and finally cosine theta divided by r. The inverse of this transformation can also be worked out in terms of the derivatives of the coordinates. Now, the derivatives of the x and y coordinates in terms of the r and theta coordinates, and you get this following result: cos theta, sine theta, negative r sine theta, and r cosine theta. Since these are the transformation matrices that relate the basis vectors, you can infer how the r theta basis vectors can be expressed in terms of the Cartesian basis vectors Ex and Ey. And the matrix that will be relevant here for transforming from the Cartesian to the polar coordinates is this lambda mu alpha prime matrix, which is the one that is applied in equation 2. And this is the relevant equation because we are going from the S frame, which in our case is the xy coordinate system, to the prime frame, which is the polar coordinate system. So that is why you will use this cosine theta, sine theta, negative r sine theta, r cosine theta matrix. Notice that even though Ex and Ey have constant components, as we showed in the first lecture, namely either ones or zeros, r theta basis vectors no longer have that property. In fact, the r theta dependencies are now explicit. So you can anticipate that if you were to take the derivative of Er with respect to the radial coordinate or the angular coordinate, you will actually pick up non-zero terms, unlike the Cartesian basis coordinates. And that is why the Christoffel symbols in this case will be non-trivial. So that is what we will illustrate in the following page. So once again, we recall that the derivative of the basis vector is expanded in terms of Christoffel symbols as shown in this new equation 1. From the previous page, we know Er and E theta in terms of Ex and Ey, whose directions and magnitudes are not changing, meaning those of Ex and Ey. But for Er, E theta, they are changing. So as an example, let us first consider the derivative of the basis vector Er with respect to the radial coordinate. How do we infer this? You go back to equation 1 and set mu equal to r and nu equal to r, because that is what we get from this expression here, which means that this will allow us to figure out the Christoffel symbols with mu and nu set both equal to r. Alpha is summed over. In this case, we are in two-dimensional space, so alpha will take values of r and theta. But if you look at equation 2, when you take the derivative of Er with respect to the radial coordinate, you notice that this quantity only has theta dependence. There is no radial dependence, which is why the derivative of Er with respect to r has to be 0. Going back to equation 1, you connect that, therefore, gamma alpha rr summed with E alpha has to be 0. This in turn tells us that gamma rrr and gamma theta rr both have to be 0. In other words, gamma alpha rr has to be 0 for all allowed values of alpha, which are just r and theta in this simple example. Let us work with this a little more until we get completely comfortable with Christoffel symbols and how they can be deduced by taking derivatives of basis vectors. So in the second instance, I take the derivative of Er again, but now with respect to the theta, the angular coordinate. What is it in terms of the Christoffel symbols? We know how to get that. We go back to equation 1 and we realize that mu now is r, because we are still working with Er, but x nu has to be the theta coordinate. So, nu is the theta index. That means, in the Christoffel symbol now we will be able to figure out hopefully gamma, alpha, r, theta, because mu is r and nu is theta. Okay, but alpha can be r and theta. So, there are two Christoffel symbols that we hope to get some light shedded on. So, if you look at equation 2, the angular derivative of ER is non-trivial now, and that is because it involves cosine theta and sine theta. If you take the derivatives, you get negative sine theta, which is written here, and the derivative of sine theta is cosine theta, which is written in the second term. And this whole expression is gamma alpha r theta summed with E alpha. But again, going back to equation 2, you realize that this expression can be conveniently re-expressed as just E theta divided by r. Okay? And that is because E theta itself is, r multiplied with what we had here from the derivative. Hence, the gamma has to be non-zero only when E alpha is E r. I am sorry, E theta, because there is no E r piece in this expression, which means that the coefficient of E r in this expansion has to be 0. So, that further sheds light on the fact that gamma r theta is 0. That is because the coefficient of E r here is 0. On the other hand, gamma theta r theta is 1 over r, and that is because 1 over r is the coefficient of E theta, which must be the multiplied with gamma theta r theta. So, this is how we figure out two other Christoffel symbol components. To complete the process, we have to take derivatives of the E theta basis vector with respect to r and then with respect to theta. I am going to show one of them. When you take the derivative with respect to the radial coordinate, once again equation 1 tells you that mu is theta now, but nu is the radial coordinate r. Alpha is summed over. We go to equation 2 to take the derivative of E theta with respect to the radial coordinate, and that is non-trivial because radius r is involved in this expression. When you take that derivative, you get where the cursor is here, negative sine theta E x plus cosine theta E y. Once again, this is manifestly 1 over r times E theta as seen in equation 2. And like in the previous case, here again you do not have the E r piece in the expansion, which means that the coefficient of E r must be 0. The coefficient of E r, as you can see here, has to be gamma r theta r. Therefore, gamma r theta r is 0. On the other hand, 1 over r must be the coefficient of E theta in this Christoffel symbol expansion. Therefore, gamma theta theta r, alpha now being theta, has to be 1 over r, which is what we worked out. So, you can again take it as an assignment to figure out what the derivative of gamma E theta is with respect to theta. That will be non-trivial because E theta depends on theta from equation 2. So, you can show, however, that gamma r theta theta will be negative r and gamma theta 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 will be 0. This will then complete all the Christoffel symbol component extraction for this simple two-dimensional coordinate transformation in flat space, namely from the Cartesian coordinate system to the polar coordinate system. In general, we would like to have maybe a more powerful method where, for example, if the metric which I had introduced in the first lecture is defined for our space of interest or space time of interest, we should be able to extract these Christoffel symbols from that knowledge. How we can do that, I am going to explain later in this lecture. So, equation 1 here is once again the expression of the covariant derivative introduced earlier, but now I think this is less daunting to understand because we have a better appreciation for what the Christoffel symbols are, because the other components are just ordinary derivatives of the vector components or the vector components themselves. But in lecture 1 we studied another kind of object, which is still a rank 1 tensor, but not a 4 spacetime vector. That was a 4 spacetime dual vector, and there are real physical quantities which don't behave like vectors under coordinate transformation. For example, under Lorentz transformation, the gradient of a scalar field introduced as one example of a dual vector. So its transformation law is in fact different from that of a vector. A vector transforms contravariantly with respect to the basis vectors. A dual vector components, on the other hand, transform covariantly. And I should correct myself, it's really the components that transform, not the vectors or dual vectors themselves. In fact, vectors, dual vectors, or any of these tensors are fixed quantities. It's only the components that change from one system to another, one coordinate system to another, one inertial frame to another. So what about the covariant derivative of a dual vector? The nice thing is that you can easily work this out by realizing that you have a scalar quantity which we met before, namely the contraction of the components of a vector v mu with those of a dual vector, namely p mu. And since this is a scalar quantity, it's covariant. It's not expanded in terms of basis vectors. So therefore, its covariant derivative must be the same as the ordinary derivative, namely the quantity comma nu. Remember, comma nu is just the derivative with respect to x nu, the ordinary derivative. So there are no basis vectors in this expansion, so you don't expect any Christoffel symbols. So the covariant derivative is the same as the ordinary derivative, and that's a powerful realization because of what's going to come in a few more steps. So this ordinary derivative can be expanded by parts, just like we do here. So the first term will involve the ordinary derivative of the vector components multiplied with the dual vector components, and the second term will involve the ordinary derivatives of the dual vector. Now, in the next step, I expand the red box, okay, as shown in this second red box. So both of these components, when differentiated by parts, will involve, in the first case, the covariant derivative of v mu, and in the second case, the covariant derivative of p mu, with mu being a lower index now, because these are components of a dual vector. We still don't know what this covariant derivative is, but we are going to get there. Okay, at the moment, we are just using simple concept from calculus, namely differentiation by parts. The quantity encased in the blue box is expanded in the second step, and here I am utilizing the fact that the ordinary derivative of a vector component can be written by using equation 1 in terms of the covariant derivative of those components and this sum over Christoffel symbols and the v betas. Okay, so this is what you get from equation 1 if you move the Christoffel piece from the right hand side of that equation to the left hand side. So when you do that, you will change the sign. That is how you pick up this negative sign. The second term in the previous equation is retained without any change. So now you realize that this first piece, v mu, covariant derivative with respect to x nu, contracted with p mu, actually cancels the first term on the left hand side inside the red box. So therefore, you can have an expression on the right hand side that is linear in the vector components v mu's. Okay, all you have to do is just a couple of index swapping. So you change this contracted mu index to something different, for example beta, and you replace this contracted beta index in both places with mu. When you do that, you will get the covariant derivative of v mu with respect, the covariant derivative of p mu with respect to x nu is just the ordinary derivative p mu comma nu, now minus this Christoffel symbol contracted with p p mu, because the view mu's are the same on both sides. So, for an arbitrary v mu, it must be true that the covariant derivative of the dual vector components are expanded like this. So, there are a couple of changes here. First, the Christoffel symbol piece has picked up a negative sign. You should compare this with equation 1, right? And the second is that, okay, mu is now a lower index because it defines components of a dual vector. And also, instead of one of the lower indices of the Christoffel symbol contracted with our vector, now it's the upper index of gamma, the Christoffel symbol, that is contracted with this vector, and that is because what we are dealing with is a dual vector with indices in the subscript. So, this is a very important expression, and this is what will be required if you want to figure out how dual vector components change under coordinate transformation in a general setting, that is in curvilinear coordinates in flat space or in curved space times. One can extend this to higher ranked tensors, and we have met such tensors. For example, G mu nu, the metric, which we realized is a 0-2 tensor, right? There are other tensors, 2-0 tensors, and we will come across them later in this lecture. For example, the stress energy momentum tensor, which you have been introduced to in special relativity or electrodynamics. So, you should be able to show using calculations like the ones we just introduced, that the covariant derivative, sometimes also denoted with this nabla mu. So, nabla mu is a replacement for semicolon mu, right. So, the covariant derivative of this double indexed quantity T alpha beta, which is a 2-0 tensor, is just the ordinary derivative of T alpha beta, plus there are two terms involving Christoffel symbols now. Okay, the first one has alpha as a spectator. Okay, it is the second index on our tensor beta that goes on, or that is retained by that tensor. But the first one, since that has been taken by the Christoffel symbol, is now contracted with one of the lower indices of gamma. Now, which of the two lower indices it is, it does not matter, because as we will see in a few slides, the Christoffel symbols are symmetric under the interchange of its lower two indices, mu and nu. But this begs a second term in Christoffel symbols, because our tensor now has two indices, and both of these indices are vector indices. They are both superscripts. So, in the second case, we take alpha, we retain alpha as an index on our tensor. Remember, in the first case it was beta that we had written. So, beta is now taken over by gamma, which means it is the second index on our tensor that is contracted, namely the nu, with one of the lower indices of the Christoffel symbol. So, this is the rule for expanding the covariant derivative of 2-0 tensor in terms of ordinary derivatives and Christoffel symbols. If you add three indices, you will have a third term here, once again with Christoffel symbols, but one of its lower indices will be contracted with that third index on that 3-0 tensor component. If you have components of 0-2 tensors, for example, the metric like G alpha beta, but here I want to deal with a general 0-2 tensor component, so I call it P alpha beta. Then its covariant derivative with respect to x mu will have the ordinary derivative of the first term, and you will have two more terms, both involving gammas and both with negative signs, because that is what we saw here in the definition of the covariant derivative of a dual vector. Okay, so that structure continues for all lower ranked indices. So, for the second term, beta is retained as one of the indices of the 0-2 tensor components. It is the first one that is summed over, so the summed over index is nu with respect to now one of the only upper index of the Christoffel symbol. So, alpha now is one of the lower indices of that symbol. Mu is retained. Mu is in fact the derivative index. Okay. In the second case, you do the same thing, but you just swap alpha and beta. Okay. Of course, paying attention to the respective places in which they occur. If you had a third index, gamma, you will have a third term involving gamma nu mu alpha. So notice that the gamma symbols or the Christoffel symbols always have one of their indices as the derivative index, which in this case is mu. That was true also for the covariant derivative of the components of the 2-0 tensor. If you have a mixed tensor, for example 2-2, that would be, for example, say not t, not mu, maybe x, alpha, beta, gamma, sigma. Then in such a case you will have both of these Christoffel symbol terms, but you will have also two of these kind of terms with negative signs, and instead of the t's and the p's you will have that multi-index x tensor components. So then a little more about the Christoffel symbols. The way we have defined our covariant derivatives, we will assume is that its action on the metric is identically 0. So such covariant derivatives will be termed as metric compatible, and these are the only types we will use in this course. And if you use this property, then applying the definition of the covariant derivative on components of 0 to tensors, as we just discussed on the previous page, you can expand this in terms of those covariant derivatives. And when you carry out those processes, of course, you will pick up Christoffel symbols. You can write 3 such equations by cyclically permuting this mu, alpha, beta indices, and then by adding or subtracting them carefully, you can show that a Christoffel symbol can be expressed in terms of ordinary derivatives of the metric components as shown here. Remember, these covariant derivatives will have ordinary derivatives as well, apart from the terms involving the Christoffel symbols. So you can take this as an assignment. This expression is fairly simple and you are expected to know it by heart. The key is that the top index of the Christoffel symbol is taken as the top index of this g alpha beta entities, which are just the components of the inverse of a metric. There is a factor of half in the front. The second index on it, beta, is summed over with 3 terms appearing in the parenthesis, one of which is with a negative sign. The one with the negative sign has this metric components with the same indices mu and nu as the lower indices of the Christoffel symbol. Okay. So the derivative index, namely comma beta, which is actually derivative, ordinary derivative with respect to x beta, is the index that is summed with the beta on top on this inverse metric component. The other 2 terms are defined as follows. The first one has one of the indices, namely mu, of the Christoffel symbol. The second index is the summed index beta, and the third one is the derivative index. Okay, so this is taken again from the Christoffel symbol, the other lower index of the Christoffel symbol. So this is just the x nu derivative of g mu beta. The second metric piece is obtained from the first one by replacing mu with nu and realizing that the metric is also a symmetric tensor in its 2 arguments. So that is why the answer is the same if you replace mu with nu, which is why you expected, given that the Christoffel symbol is symmetric in mu and nu interchange, you notice that this expression given here is also symmetric under the interchange of mu nu. So that is another way you can figure out the remaining term in the expansion of the Christoffel symbol in terms of derivatives of the metric. Another important insight is that since the metric is defined in the space-time interval, right? So given any coordinate separation delta x between 2 space-time events, the metric is a projection of delta x and delta x into a scalar, which can be termed as delta s squared, as we discussed in the first lecture. And the delta s squared is known as the line interval, which is invariant under coordinate transformations, in special relativity under Lorentz transformation, right? So that means that yeah, the metric is an important quantity because it allows us to define those invariants. So now its derivative tells us how that interval can change, let's say not only under coordinate transformations, but also, for example, if the space-time is curved and you're translating those 2 points. This can happen if you drop 2 balls, as in an elevator, right? As the 2 balls fall, and this is a static elevator to begin with, under the influence of Earth's gravity, these 2 balls are going to come closer because they're actually going to fall radially towards the center of the Earth, right? So that is in fact a manifestation of Earth's gravity. But if you actually had 4 balls, so 2 other balls vertically separated, then as this constellation of balls falls under Earth's gravity, the 2 vertical balls are going to be stretched more and more apart. This is again a manifestation of the tidal forces in Earth's gravity, and you can track how these distances change by knowing how the metric changes in Earth's gravity, and it's not fixed. So these derivatives are actually important in defining the curvature in Earth's gravity. It is true that you can always make a coordinate transformation so that these derivatives, even if individually they don't vanish, the combination vanishes so that the Christoffel symbol is 0. In other words, if you drop these balls, of course they're going to fall in front of your eyes, but suppose now you made your elevator fall freely in Earth's gravity, then you're in the same frame, okay, locally at any given space and time point, where these balls, they freeze for you because you're in their frame. Although your friend standing on any given floor in the building will see all of you fall at any given time with the same speed, right? So locally in space and time, you can get into a frame where you can make this Christoffel symbol vanish. So however, if you wait long enough, you will actually see the separation between the balls change, and that tells you that although momentarily you could get the effect of gravity to vanish, you could not do so globally, that is over separated times or space points. And that comes from the fact that if you take a further derivative of this Christoffel symbol, and that will now involve double derivatives of these metric components, that cannot be set identically to 0 for all of these components if you are indeed in a gravitational field. And which means that if you want to claim that gravity is nothing but the manifestation of space-time curvature, then you will have a situation where curvature has to involve, or the definition of curvature has to involve has to involve another derivative of the Christoffel symbol. So 2 derivatives of the metric components. So I alluded to some of these properties, but go ahead and show that the metric components are symmetric under the interchange of their 2 indices. So G alpha beta is equal to G beta alpha. Similarly for Christoffel symbols, and this is maybe easier given that we have introduced the Christoffel symbol in terms of the metric and its derivatives, that the Christoffel symbols are symmetric under the interchange of these 2 lower indices, mu and nu. So how are we going to go to curvature from here? The elevator discussion sets the stage, but in terms of mathematics, what we need to do is know how to transport a vector, for example the 4 velocity vector, of a particle along its path. And this path could be the shortest path given that can occur between any 2 points on its trajectory. And if you are dropping a ball under the influence of Earth's gravity with no other agents influencing its motion, then it will travel the shortest path possible between any 2 points on the trajectory. But in general, it could actually be an extremal path. So shortest paths are what we will eventually define as geodesics, but the path connecting any 2 points that is not necessarily short, but could also be the longest path, that is also defined as a geodesic. So, in general, the extremal path connecting any two space-time events is the geodesic between those two points. And the geodesic is not only an extremal path, but it's also the straightest path that a particle can take as it is circumnavigating around in space-time in some curved situation. And this curvature could have been created because of the presence of another massive object, for example, the sun. So, this then begs the question, well, how do you define straight? Okay, a path is straight if, or let me backtrack. We say that a particle is moving along the straightest path possible between any 2 points if its forward velocity vector does not change relative to the tangent vector on that path. Now, I am going to replace the term path with a curve, by which I will mean a parametrized path. So, you can have 2 points of interest, call them A and B, and you can have a path connecting these 2 points. But if you parameterize it with some parameter, for example, the proper time, which could be measured by the clock being carried by this traveler, or in general it could be not tau, but some other parameter lambda. Okay, so, lambda is the parameter that defines how much you have covered in traversing this path, right. So, this parameterized path is what we will term as a curve, and so there could be markers here which give a certain number of units covered in the value of lambda in going from A to B. This curve has different tangent vectors at different points. Let me choose an intermediate point here, and at that point the tangent is given by that vector. At a different point it will be a different vector. For the moment I define this tangent vector as u. Okay. Really it should be bold-faced u, as I have shown in my notes. So, we say that this curve is a geodesic if it transports its own tangent vector, namely u, in such a way that u never changes. But in general you say it parallel transports an arbitrary vector v if the direction and magnitude of v relative to u does not change along this curve connecting A and B. So, that is the basic idea behind parallel transport, and it is important to define a geodesic. So, let us go over this once again. To define the fact that an arbitrary vector is parallel transported along this curve, we say that this vector will not change along with respect to the parameter on this curve. So, as lambda increases, you will see no change in v in magnitude or direction, right. But how do you define that in terms of the tangent vector at any given point? Because it is a local property, right. It has to be satisfied at every point of this curve. You do so by realizing that d by d lambda of v is nothing but the projection of the covariant derivative of the components of v on the tangent vector. Okay. In other words, you take the covariant derivative of v alpha with respect to x beta, and then you contract that derivative with respect to u, and so the components of u are u beta. Okay. Symbolically, this is the same as the derivative of v with respect to lambda, which is the same as this covariant derivative with respect to u of the vector v. And if this is 0, you say that v, the 4 vector, has been parallel transported along a curve whose tangent vectors are u. A geodesic is a curve that parallel transports its own tangent vector, which means here this equation is satisfied with v replaced by u itself. In other words, the covariant derivative of u projected on u is 0, and in terms of components, that means that u beta contracted with the covariant derivative of u alpha is 0. But what is the covariant derivative of u alpha with x beta? That we know because we have expanded covariant derivatives in terms of Christoffel symbols. So, we just replace that covariant derivative in terms of the ordinary derivative of the vector components and this Christoffel symbol term. Notice that there are two contractions here, one in mu and the other in beta, and this has to be equal to 0, and that would be the equation of a geodesic. So, this can be written in terms of derivatives that we are familiar with, namely derivative with respect to parameter lambda. If you notice that u alpha itself is the derivative of space-time coordinates defining this curve with respect to lambda, the parameter on this curve, right. But then you project this derivative on u beta, and that projection, as we learned here, is another derivative with respect to lambda. So, this is all of that first term on the left hand side of that equal to sign. The second term is simple because the u's are nothing but the derivatives of the space-time coordinates with respect to the parameter on the curve lambda. Okay, once again, lambda here could be the proper time of any massive particle, a massive clock. So, this is the equation of a geodesic, and this arises from the definition that a geodesic is the straightest possible path between any two space-time events. But you can take it as an assignment to show that you will get the same equation if you started by saying, all right, a geodesic has to be the extremal path. So, the maximal or the minimal path, or it's a curve with the maximum or minimum distance between any two given points. If you utilize that definition, that will actually require in some integral calculus, but you can, and then variational calculus, like you have studied in classical mechanics. So, if you apply that to any small interval ds squared expanded in terms of g mu nu contracted with dx mu dx nu, if you were to then differentiate all of that with or divide it with respect to d lambda square, and then integrate that over any piece on this curve, call it d lambda, you can show that if you vary that length so that the variation is 0 with these fixed points, then you will obtain the same equation. So, it is great consistency that the geodesic is indeed the straightest path, but also the extremal path between your space-time events of interest. So, I already hinted at the fact that we are going to study curvature today, and that curvature can be expected to be defined in terms of the derivatives of the Christoffel symbol. So, in other words, it will have to involve double derivatives of the metric, because the Christoffel symbol itself involves single derivatives of the metric. But conceptually, what is curvature? For that, you don't necessarily have to go to 4-dimensional space-times or even high dimensional space-times, if that is what your theory of interest would require. But you can once again begin with just a 2-dimensional space which is curved, and a sphere is one example of such a curved space. One way to know that is that you draw a triangle comprising of sides that are all along geodesics, and a sphere has these great circles as geodesics. So, all of the longitudes are geodesics. The latitudes are not geodesics unless you are on the equator, which is actually another great circle, just like any of these longitudes, and they all have the same radius. Remember, these latitudes have shrinking radius going all the way to 0 at the 2 poles. So, here you have a triangle. This is one side of the triangle, and it is on a longitude. So, that is a part of a geodesic. This is another side, the second side of the triangle, which is also on a geodesic, namely the great circle, and then you have this third side, which is on the third geodesic, another longitude. One test of whether this triangle is on a flat space is to just add up the internal angles. In this case, the way we have drawn things, this is a right angle, because that is the angle all longitudes make when they intersect the equator, and that is another right angle. So, you already have the sum of these two angles as 180 degrees, and the moment you require these two flanks of the triangle to be separated even ever so slightly, you introduce another angle here at the pole which is non-zero, which means right away that the sum of these three angles has to be greater than 180 degrees. And you know from Euclidean geometry that the sum of the internal angles of a triangle in flat space is exactly 180 degrees, not a bit more, not a bit less. Here the sum is more, and this is a positively curved space. If it were 0 flat space, it will be 0 curvature space. If the sum were less than 0, that would be negatively curved space, a hyperboloidal space. All right. So I should be able to use a space like this to define curvature. The problem with the internal angle of a triangle definition is that it sort of requires me to you take a somewhat more global picture of my manifold, or set of points of interest on this space. And but it will be helpful to actually be at just one point and define curvature locally at that point. And local definitions are facilitated by derivatives. So, how do you use derivatives to define curvature? So, I am going to go in that direction as a limiting case. I will start by realizing that, okay, when you take a vector on this triangle, right. So, maybe you start off here, you take a vector up along this first flank or first side of the triangle, you parallel transport it. If you parallel transport this vector, you land up at the equator and you get this vector. Okay. If you are an ant, you will notice no change because all along this vector is remaining tangent to your curve of interest, namely that longitude. Now, you ask your friend to parallel transport this. Actually, well, you can do this yourself. Once you reach the pole, you parallel transport this vector on the second side of the triangle, which is another longitude. So, parallel transport means that you are now going to carry this vector with you so that it does not change in magnitude or orientation with respect to the tangent on this second side. And so, this is the new set of vectors you will get, okay, when parallel transported back to the equator. And then finally carry this vector on this equator, okay, back to the point at which you started, that original point. So, this again is parallel transport. But once you land up here at that original point where you set out, you have noticed that you have managed to change the orientation of this vector. It is no longer oriented along that first longitude, and this amount of change actually tells you how much the curvature is. But the curvature is not only defined by that change, but also by how big your vector itself was, okay, or how big this path was. So that is another way to introduce curvature. Essentially, it comes from the fact that you can now imagine a situation that instead of this triangle, you actually transported this along some relatively small parallelogram. All right. And once again, when you transport this vector along the sides, the four sides of the parallelogram, you come back and you realize that the vector actually has changed relative to its initial state. So, that statement can be translated as follows. Moving the vector along as the first side, okay, upwards, let's say, of the parallelogram, and then the second side is like action of two covariant derivatives on your vector of interest. I am not showing this explicitly, and that's because this course is more like a revision, I believe, for most of you. But either you trust me on this, or you look up some textbooks, for example, the one by Robert Wald on general relativity, or Bernard Schutz on first course in general relativity. But what you can show is that transporting your vector along the first side of the parallelogram and then the second side is like the action of these two covariant derivatives on the vector, and then parallel transporting your vector back down the third side and then the fourth side is like these two vectors but in reverse. But if your space-time is curved, then this reverse action of these derivatives on the vector does not compensate for the change in the vector when you carried it in the along the first two sides of the parallelogram. So if this net action is not zero, that is tantamount to the fact that your space-time is curved. And therefore, this quantity in general is equal to a new quantity, not a Christoffel symbol, but this is something we call the Riemann curvature tensor components, and this is of rank 4 tensor. So this difference of the actions of these two covariant derivatives on the vector is in general not zero, but is proportional to the curvature of your space-time or space, and that is defined by this curvature tensor. But this amount of change is also proportional to how big your vector was to begin with, which makes sense. Now, this definition tells you automatically that another way to write it is you act on a vector's components, two of these covariant derivatives, but then you antisymmetrize over these two derivatives. So basically the alpha and beta indices. Okay. Now, antisymmetrization, the way we introduced it in the first lecture, also involves a factor of half. So you have to take care of that, but that's just a definition. So it would be half of this quantity will be defined as the antisymmetrized action of these two vectors, antisymmetrized over alpha beta acting on v mu. All right. But the definition of the curvature does not have that extra factor of half. So you'll just have to carry it carefully in your work. So this action is equal to Riemann curvature tensor contracted with v nu, but because of this antisymmetric aspect of this definition in alpha and beta, it is automatic that this Riemann curvature tensor component is antisymmetrized over alpha and beta, which means if you swap alpha and beta, you will pick up a negative sign. So keep that in mind. Now, this itself is useless unless you are able to express it in terms of the metric, because once again the idea is that if you have knowledge of the metric of your space-time, then you can calculate the Christoffel symbols by taking the first derivatives of the metric. And if you know the Christoffel symbols, then is there any way you can work out the Riemann curvature tensor components in terms of them? And the answer is yes. That again you can take as an assignment. You know what the covariant derivative is of a vector in terms of the Christoffel symbols. When you take a second covariant derivative, that's going to act on all of the objects involved in the first one, which will involve ordinary derivatives but as well as Christoffel symbols. So eventually you can express this Riemann curvature tensor component in terms of the Christoffel symbol, so first derivatives, as well as quadratics of the Christoffel symbols. You will notice that this expression is antisymmetric under the interchange of the last two index. So in this case mu and nu. Okay, that is a test whether your expression is correct or not. So specifically, you can find the first term in this expansion by retaining alpha and beta on this Christoffel symbol in their original spaces. So superscript and subscript, but swap the mu and nu and introduce a comma in between. So this is the same thing as saying you take the ordinary derivative of gamma, alpha, beta, nu with respect to x mu, the space-time coordinate x mu. The second term is obtained with a negative sign by swapping mu and nu. So now mu is in nu's place and nu is in mu's place, and that is expected because r alpha beta mu nu is antisymmetric in mu and nu. You get the third term by realizing that okay, you will have quadratics in gammas, but your gammas cannot have the mu nu, any of them, because gamma itself is symmetric under the interchange of its lower indices. So, if you have both mu and nu on a gamma, it has to vanish. So, automatically the first one is selected by using beta and nu. All right. So, that is what you have here. The top index is a dummy index that you sum over. So, this sigma index is summed over with the second gamma in this quadratic term. Okay. So, the second gamma Christoffel symbol has sigma, that dummy index, as one of the lower indices, but you have accounted for only beta and nu, the two lower indices in the Riemann curvature tensor. So, the third index has to go somewhere, the mu index. So, that is what comes as the second index, the second lower index of this second gamma term. Okay. Alpha is the remaining top index on R. So, that also has to go somewhere. So, that is what is taken up by this second gamma. So, this is how you define this quadratic. The second piece in quadratic is easy because it has to be governed by the fact that R alpha beta mu nu is antisymmetric in mu and nu. So, you obtain this by switching this sign to a negative sign and replacing your mu and nu. So, wherever you had a nu before, you have a mu now, and where you had a mu before, you have a nu now. All other indices are just spectators. So, this is your Riemann curvature tensor components, all expressed in terms of the Christoffel symbols. So, I showed you an example of how you can calculate the Christoffel symbols knowing the basis vectors, but you also have an expression for the Christoffel symbols in terms of the metric. So, if you use them, you can therefore infer the components of the Riemann curvature tensor. Now, for ease of use, we sometimes lower this top index using the metric. Remember, in the first lecture we showed that you can use the metric to raise or lower indices. So, in this case sigma is summed over, alpha is a free index on both sides. So, this is how you define, we colloquially call all of these objects components of Riemann curvature tensor, but they are really different types of tensor components, because here all of the indices are lower. Okay, alpha has now come down. But this kind of an object has some other interesting symmetry properties. One of them is that this object is antisymmetric under the interchange of not just mu and nu, which is a property it carried over from this initial object, but also under the interchange of alpha and beta. Okay. And finally, this quantity is it is symmetric under the interchange of the pair alpha beta with respect to the pair mu nu. Okay, this is all written here for your benefit, but keep these properties in mind. This is important because of the following reason. As you see these indices proliferate, you may actually be getting very worried, because you will be imagining that, oh my goodness, there are so many components to compute the moment you know the metric. Metric itself was somewhat difficult because metric is a two indexed object. So, in 4 space-time coordinates, you imagine that the metric components will be 16 in number. So, that is 4 times 4, but because the metric is symmetric under the interchange of its two arguments, thankfully only 10 of those 16 components are independent. Okay, but 10 is a big number, but it is a manageable number. So, note that given any space-time, okay, it can be defined by a metric, and that metric has at most 10 independent components, okay, in 4 space-time dimensions. Then that is because n times n plus 1 divided by 2 is the number of independent components for an n cross n matrix. If n is 4, the number of independent elements has to be 4 times I'm sorry, it was n times n. Am I doing this right? Yeah. So that is 4 times 5, because n plus 1 is 5. Okay, divided by 2, that is just 2 times 5, which is 10. So, that is good. What about the Riemann tensor? Okay, here the fact that this is antisymmetric in mu and nu means that combinations of mu and nu that are independent will not be 10, okay, in 4 space-time dimensions, but only 6, and that is the property of an antisymmetric 4 by 4 matrix, right. So, 6 there. Similarly, for alpha and beta, another 6. Now, if that was the end of the story, then 6 times 6 will give you 36 independent components. But the fact is that this is also symmetric under swapping of alpha beta with mu nu. So if you carry through all of those symmetric properties, you can show to yourself that R alpha beta mu nu has only 20 independent components, and that's much more manageable. So that is the case for a general 4-dimensional space-time. Moving on. So because of this, we can actually express the Riemann curvature tensor in terms of derivatives of double derivatives of the metric. Now, I gave you the general expression in terms of covariant derivatives in the previous slide, but if you again manage to move into a local frame, actually I'm sorry, I should so this is a general expression for the Riemann curvature tensor in terms of the Christoffel symbols and the derivatives. But yes, if you manage to move into a local frame like that, freely falling elevator where you were moving with the freely falling constellation of 4 balls, you will you can simplify this expression where R alpha beta mu nu are completely given in terms of double derivatives of the metric. Okay. Here again you can remember this expression very easily by remembering the symmetry properties of R alpha beta mu nu introduced on the previous page. But sigma mu nu coming after the comma basically means that this is a double derivative with respect to x sigma and x nu, and similarly for the other terms. Using all of this, you can show that the R alpha beta mu nu's actually obey another identity, and this is known as the Bianchi identity, where its covariant derivative with respect to x lambda, when summed with again a cyclic permutation of the last 3 indices, this sum is equal to 0. So the way I've defined this is I've focused on the last 3 indices mu, nu and lambda, where the final one, the 5th one in this combination is a space-time derivative, right? So you start with this and then you move lambda to 3 places up and move nu back like this by a place each, right? Then that is how you get this middle term, and for the last term you move nu up by 2 places and move lambda mu back by 1 place each, right? So the sum of this combination is 0. This just comes from the earlier definitions of the Riemann curvature tensor. So in fact, in working out the independent components of R alpha beta mu nu, this is one other constraint that I didn't talk about, but all of those combined actually leave you with only 20 independent components of this tensor, which is great. This is known as the Bianchi identity, and this in fact is like conservation. It's a geometric property, but we will utilize it eventually to define Einstein's equations in a few more slides. Some contractions can help things. So we dealt with contractions in the first lecture briefly. Now that we have tensors with multiple components, indices, contractions can simplify life. Contractions are one way to generate new tensors from old tensors, and one such example is that, yes, you go back to this Riemann tensor R alpha mu beta nu. If you contract the first 2 alpha mu, you get 0. Why? That is because G is symmetric under the interchange of its 2 indices, but R alpha mu is antisymmetric. So if I were to contract this quantity with G alpha mu, not beta but mu, then you will get a 0, because the contraction of a symmetric matrix with an antisymmetric one is 0. Similarly, the contraction of G beta nu with R alpha mu beta nu would also be 0, because Riemann curvature tensor is antisymmetric in the last 2 arguments. Therefore, the only one meaningful contraction you can do is between the first and the third index. Another meaningful would be between the second and the fourth index. Here, let's just focus on the first and the third. So I contract with G alpha beta. The remaining free indices are mu and nu. You get a new tensor, very much along the lines of G mu nu, G mu nu with mu nu down were the components of the metric tensor. Here G alpha beta is the component of the inverse metric tensor, but R mu nu is a 0-2 tensor, very much like the traditional G mu nu is. All right. So this is called the component of a Ricci tensor. If you further contract R mu nu, the components of the Ricci tensor, with another action of this inverse metric tensor G mu nu, then both of these indices are contracted. You have no free index left, uncontracted index left. So you get a Ricci scalar, which is scalar under coordinate transformation. So this quantity, the Ricci scalar and the Ricci tensor components R mu nu can be combined to form another 0-2 tensor known as the Einstein tensor. So the G mu nu Einstein tensor, this is the big G mu nu, is equal to the components of the Ricci tensor minus half the metric tensor G mu nu components times the Ricci scalar. Why is this useful? We will meet it in a moment, but because so one preparation for it is this problem. Because of the Bianchi identity we met with on the last page, you can show that if you do some contractions here, and contractions of covariant derivatives is easy because of metric compatibility of a covariant derivative. So you can easily move the small g mu nu inside or outside a covariant derivative because the covariant derivative acting on the small g mu nu is 0. So, but you will need to do some contractions to recast this Bianchi identity to involve ultimately only the Einstein tensor, and at that point you will find that this kind of contraction of the covariant derivative of the Einstein tensor is identically 0. Why is this useful? It is useful because if you want to create curvature or a curvature like quantity such as the Ricci tensor or the Einstein tensor from the stress energy momentum tensor, which is T mu nu, something I mentioned earlier, then because the stress energy momentum of any fluid distribution is expected to be conserved, it automatically means that if you are setting T mu nu to be proportional to R mu nu or G mu nu, then that object also has to have a vanishing covariant derivative. And this Bianchi identity prepares us for that. In fact, you can show that you cannot have this kind of a property shown in the red box hold if you were to replace G alpha mu with the Ricci tensor components R alpha mu. Okay. So that is what I will discuss in a moment. It is therefore actually heartening to have a geometric quantity that obeys this property, where its covariant derivative contracted in this fashion is identically 0. This is the property that we will use in obtaining a relation that connects a curvature quantity to the stress energy momentum tensor of any fluid distribution. This is what Einstein did, but before I do that, I'll have to introduce some examples of the stress energy momentum tensor, and that is what I'm going to do in the next lecture.